Hi everyone, I started streaming. I hope you can hear me. If you hear me, can somebody please type yes? Awesome, thank you, Giselle. Thank you. Just one more minute before I start the lecture. Okay, so I'm going to start the lecture because today is a long lecture and I still want you to do some exercises at some point. So let me start. The topic of this week is data representations. I hope that you have all done watched the videos that I posted for Tuesday. And I've seen that most of you have done the quiz associated with those videos, so you have an idea for what I'm going to talk about. But I just want to cover this sort in a little bit more detail and give it a broader context, because this can be a little strange for those of you who have never really been exposed to computer science. So here's what I'm going to talk about. In computers, numbers are everywhere. So computers are literally, the little machine that you guys have been working on for Project One. It's a pretty faithful model of what a real computer does. And basically, what you need to have in mind is that what the computer does is number manipulation. It's arithmetic, logic operations, basically deals with operations with numbers. But of course, we as humans are not so interested about numbers. Of course, if you're in the stock market or something like that, you probably are. But we are more interested in things like, text, images, sounds, the things that are part of our human world. Compound data like medical records, bank accounts, all of that stuff. And that's, one way or another, all of those things that we care about are represented in our modern society as written things in text or images or even sounds. And so the corollary of this is if we want to use computers to do processes that apply to our world, the real world, then we have only one option, is that we have to convert from the representations that we are used to, like text and images, to numbers, because that's what computers do. And then once the computers do whatever they do with the numbers, then they need to show us back again the things that we understand, like text and images and audio and things like that. So basically, and this is a principle that applies to absolutely everything, right? The computers don't understand anything other than numbers. And so, but the interesting thing is that there's ways of mapping the things that we care about into numbers and then back again. And that's the topic of today's lecture. So today's lecture is about um, the representation of things as numbers, and these are called the word that people use technically is called encodings. And then the second thing is the representation of the numbers themselves as physical effects that are capable of being operated on the physical hardware, right? So there's these two things, and sometimes one thing that I noticed in the videos that you guys watched is that they kind of blur the line between those two things. It makes it a little bit confusing, and I wanted to introduce this distinction. It's really two things that are going on. One is the encoding of the things that we care about as numbers, okay? And then there's a second mapping, which is encoding those numbers in ways that can be manipulated by physical hardware in some way, some manner that can be represented in physical quantities that represent those numbers, okay? So that's what we're going to talk about. So let me start with the the first part, encodings, which is a representation of the things that we care about as numbers. So what are these things? Let's start with text. Okay, text is a pretty obvious thing because we live by and large with written documents, and those are, we use letters, we use digits, we use punctuation, and there's all sorts of extended alphabets out there. There's non-Western alphabets and symbols. So there's lots of written symbols that we as a civilization have evolved to use, and so we need to be able to encode those symbols that we care and know about in some form of number so that the computers can manipulate them. Okay, so one of the most widely used encodings is what's called ASCII. The ASCII stands for American Standard Code for Information Interchange, and the word American there really denotes the fact that the first real sort of commercial computers were really developed in the United States. And so the first need to do these encodings was really the need to encode the English language and the English characters. Um, the ASCII stands for the American Standard Code for Information Interchange, and these are text encodings that represent the textual symbols as numbers. So basically, it's a table that says, okay, here's the character. All right, so it looks. Hold on, let me make a little interruption here. It looks like there's some technical difficulties. Um, Can people hear me and see me okay on Twitch or in the screen? Is it only some people who have problems or everybody's having problems? Giselle, you can see me good. Mm-hmm. Okay. The tennis button. Let me see what is going on here. So it looks like the north side auditorium is okay. In here, let me see. I'm on the south side auditorium. Let me try to play. I can see myself. I can see myself on the south side auditorium. Okay. All right. So I guess that if you just cannot make the screen work, just please watch directly on Twitch. Okay. So you can try to sit down first. If that doesn't work, and press the play button on media on the top right corner. And if that doesn't work, just go on Twitch and watch the video there. All right? The attendance button should be there. So we'll figure all that out when we make the value. So if you guys cannot see the attendance button, don't worry about it. We'll figure it out when we do the little break for doing the class activity, okay? Maybe just a matter of the draw distance, that you have a small draw distance that if you're far away from the stage, you won't see the button, okay? All right, we'll figure that out when we do the little break for the classroom. Right now, if you have problems with the in-world screen, try perhaps changing your draw distance, moving to a chair that's closer to the screen. Maybe that will work. If not, just watch it on Twitch. Let me just type here. Okay, I am going to continue. The good thing is that the video will be stored and you can watch it later, but hopefully everybody will be able to catch up. So I was talking about text encodings and ASCII. So the first approach to this was just a regular ASCII encodes the Western alphabet, that's numbers, punctuation, and other special characters, basically 128 characters. That was the first batch that was encoded in ASCII. And then pretty soon, it was pretty clear that at least some European languages have like accented characters and stuff. So more characters were needed, and so that's the extended ASCII that comes into play. So you have the vowels with the little accents on them and all sorts of other characters that are used in Latin languages. So that added another 128 characters. So we have 256 on extended ASCII. And then finally, more recently, it was pretty clear that it being so centered on the Western alphabet was not a good idea, because there's lots of other alphabets and lots of symbols, like the Asian languages that have thousands of symbols. They didn't fit in just even the extended ASCII encodings. So people came up with the Unicode encodings, which have a lot more bigger numbers, and so you can encode pretty much all the symbols of all known human languages these days, including emojis. So now emojis are native character encodings. Oops, let me go here. So here's a typical table that you can find out there on the web of how these encodings look like. It's basically, you have the character over here. Here's the characters over here. And then this continues. And then you see here the numbers that are given to these characters, right? So here's the numbers that are given to these characters. So for example, if you zoom in here, you see that the @ sign is number 64. The capital A is number 65. The capital B is number 66, etc. This is convention, okay? This is the people that just decided, okay, let's encode the numbers and the letters and the punctuation like this, all right? So we just need to consult these ASCII tables to find out what's the number for a given character. So what happens when you press, you have a keyboard. What happens when you actually press the character, for example, capital A? You see capital A on the keyboard because its keyboard is facing us, human people, but the computer doesn't really care. All the computer cares about is that the A is encoded to some number. In this case, it's going to be the number 64 in ASCII. And then internally, that's what's going to be used to encode the character capital A. Okay? There's no capital A anywhere inside the computer. There's just the number 64. Now, when we want to see that character, of course, this is going to be translated into a representation that we can understand. So it's going to come up as the picture A in the screen, so that we can understand that that's an A. But this is just all of these peripherals like the screen and the keyboard, they are facing us, right? So we need that help. But for the computer, it doesn't care. It's just the number 64 that's inside. And it does everything that it does with the other numbers. It can add them, subtract them, divide them, do all sorts of things with just any other regular number. So what about images? So here's a nice image of a little puppy. What are images really? The images are again just numbers. So if you zoom in, what's really going on in digital images is that there's a grid, very much thinner than what I'm showing here. And what that means is that these are called the pixels. Each one of these little cells is called a pixel. And what's a pixel? A pixel is just a little piece of information of numbers that represents a color, right? So that each pixel has a color associated with it. And so what's a color in computers? Computers also don't understand colors. Colors is for us. So what's a color? A color is just a trio of numbers, just three numbers. And what do three numbers represent? They represent the mixture of red, green, and blue. And again, it's a long history for how the human visual system works, but it turns out that if you have just three colors, red, green, and blue, and if you mix them in different intensities, you can compose all the colors in the world. All right, that's sort of I don't really understand, but that's how the visual system works. There's like these three primitive colors, red, green, and blue, and if you mix them all together, you get all the colors that we can perceive. So what is a color? A color for a computer is just a trio of numbers that gives you the intensity of red, the intensity of green, and the intensity of blue, right? That's what each of these pixels represents, is a trio on numbers. So what are image encodings? Image encodings are numbers that represent images, and in particular, like, okay, Arkin has a question. Why do pixels use red, green, and blue? That's a good question. So that comes with the human visual system, okay? So it turns out that the way that, and I don't know very well because this has to do with more cognitive science than with computer science. But it turns out that if you mix red, green, and I guess this is known by the painters for a very long time, if you have red, green, and blue as paints, mixing these three colors can give you all the colors that you want, and mixing in different quantities. Okay, so again, this is known before computers existed. Okay, this is a technique that painters know about. So if that, basically painters were able to identify these three primitive colors upon which all the other colors can be created, okay, which is really amazing. Okay, so if you think about like purple, for example, purple is going to be some combination of red and blue, right? Some yellow, I think, is a combination of green and blue or something like that. I don't remember. So, but you can have many shades of yellow by altering the intensities of the green and the blue. Okay, and so literally, if you look at your screen in your computer right now, what your screen is the screen itself, the hardware of the screen is made up of tiny little LEDs, so lights, okay, LEDs that each one has an intensity for red, an intensity for green, and an intensity for blue. And this is really amazing. It is tiny microscopic little LEDs, little lamps that light up in different intensities of red, green, and blue. And given that mixture of red, green, and blue, then that's how we perceive, the colors when we look at the screen. Okay, it's quite ingenious. Okay, the way that people have kind of realized how to make this hardware do whatever we want it to do. Does that answer the question? All right, so basically image encodings are numbers representing colors in each of the pixels of the screen. So when you probably all have heard about the resolution of pictures, right? You have a picture that is a 1080 by 780, okay? That means how many pixels we have on the horizontal axis versus the vertical axis, right? It means the size of the grid, how many pixels you have. That's what those numbers mean. So image encodings take an image, and then they not just assign red, green, and blue values to each of the pixels, but that's the most important thing that all image encoding formats do. It's all the combination of red, green, and blue. But then they have more things around it. So whether the image has transparency or not, whether the image is a GIF, for example, is actually many images, not just one. So there's all sorts of then variations. But the most important thing, the core, is that the blob of data is this series of three numbers, one trio per pixel. So basically, if you look inside the computer, what's an image? If you see an image here on your screen, what's really going on inside the computer doesn't understand the concept of an image. So all it has is just this series of numbers. In the case of images, it's like groups of three, right? Which is red, green, blue, red, green, blue, red, green, blue. Each one corresponds to this pixel over here, that pixel over there, that pixel over there. So many of them. That's all there is for images in computers. Again, numbers. Computers only deal with numbers. It's up to us to figure out how to map from the things that make sense to us into numbers, and then vice versa, from numbers to things that make sense to us, because then we need to decode, right? When you pass an image around, what you are passing is these numbers, right? When you download a picture, as you are watching right now, video on Twitch, what your computer is receiving is a series of numbers. Videos basically are a stream of pictures to some order of approximation. Okay, frames are basically static pictures that come and give the illusion of movement. But basically, what is this? It's just numbers, and in particular, these triplets that corresponds to the mixing of red, green, and blue. That's how you are able to see my face as sort of a beige-like color and my chair as a black color. That pixel over there, this pixel over here is black, okay? So each pixel has associated a color. Sounds. What are sounds? When you play music, what is that? Well, again, it's numbers. And how do you encode sound into numbers? Well, sounds are waves, right? So sounds are waves that correspond to air pressure. So as we are speaking, the air contracts and expands according to our voice, right? And so those waves, if you lay them out mathematically, these are this intensity of pressure, right? Intensity of pressure in air. And so what is the sound? How do we encode? What's digital sound? How do we encode this? Well, we just sample, okay? Sample fast enough, and we just say, okay, this is -4, 0, 4, etc. So we have basically a series of numbers that correspond to the air pressure at that particular point in time. Okay, so when you pass music around, it's this series of numbers that correspond to air pressure. And so when these numbers reach your loudspeaker, the loudspeaker then knows how to translate those numbers into actions of the diaphragm of the speaker in order to be able to produce those airwaves, to reproduce those airwaves according to the series that I am generating here. Right? I am generating a series of numbers here by speaking on my microphone. My computer is encoding these sound waves as a series of numbers, and you over there are receiving the series of numbers that my computer generates. Your computer gets those numbers and it sends it to the speakers, who are then able to decode and basically apply the air pressure so that you can hear exactly the voice that I'm producing here. So basically numbers, that's all there is. And bottom line, inside the computer, everything is encoded as numbers. And again, all you need to do is the computing machine that I gave you for the project one is a pretty decent model of what modern computers do. It's just numbers. It just adds them and shifts them around and multiplies them, and but basically it's just numbers. Okay, it's quite amazing how we can how we over time and just really in the past 50, 70 years that we were able to basically just come up with these encodings of from things that make sense to us to numbers that can be manipulated by computers. All right. Any questions about the encoding part so far? Okay, so I'm going to continue now to the second part of the problem, which is one thing is to, encode the things that we care about into numbers, but computers are physical machines. Numbers are mathematical concepts, right? You can't really operate numbers. Numbers are just abstract concepts. So what is really going on in computers? We need to find a way of mapping numbers into physical actions. That's what happens. That's the power of a computer. It's not just the abstract thing, but it's how do you represent, now that we have numbers, how are we going to act on those numbers using physical hardware, right? That's the interesting thing. So the number representations are representation numbers as physical effects. So in this technology of electronic digital computers, of which the machine that you guys have worked for, Project One, is a good reliable model. You have basically this hardware that at the bottom there's this concept of transistors, which I didn't explain very well, but basically these are gates. And the interesting thing about the transistors is that they are very good at operating under just two values of voltage, like 5 volts and 0 volts, or 5 volts and minus 5 volts. I don't remember. Some of them go between 0 and 5, others go between minus 5 and 5. It doesn't matter. But they are gates. They are on and off gates. If at some points they let the current pass, and at other points they stop the current from passing. So they have these two voltage levels. And why two? Right, so that's an interesting question. Why two voltage? Because electrical circuits, you can have any voltage that you have. Really, it's a they are continuous hardware, so it's not like it's a digital thing. But the interesting thing is that, well, we want to be able to, deal with numbers. We want to be able to encode numbers, right? And we could, in principle, construct hardware that would have many levels, for example, 10 levels of voltage. It would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now each one of these voltages would correspond to a number, for example. And then if you if you want to go beyond 9, then you put two transistors, right? It's just like we do with the numbers, right? And then you have the first transistor is for the lower order digit, and the second transistor is for the higher or the next one, right? So something like what we have in the model of the computing machine that you guys have been working with in this simulated world. And that is totally viable, and it's perfectly feasible. But it turns out that dealing with 9 different things is a lot more complex than dealing with 8, and which is more complex than dealing with 7. Basically, the simplest possible way that can work is actually just dealing with 2 things. All right, because now it's very easy. You have between 0 and 5. So if this is hardware, and hardware is not perfect, so it's not always 5. It could be 5.8, 4.8, or 5.2, or whatever. So there's these thresholds that now we can say, okay, if it's supposed to be between 0 and 5, anything under 2.5 is a 0, and everything above 2.5 is a 1, right? And now it's just much easier to do this hardware that has to do just with these large thresholds instead of having to deal with hardware that has to detect much smaller thresholds between the numbers. So that's just purely for a matter of convenience that these circuits just deal with 2 values of things. It's either on or off, right? And so now the question is, well, given that this is more convenient for designing the hardware, how do we represent numbers with just these two symbols? Right now we have just 0 and 1. How do we represent, for example, 65? Right? We don't have these nine, we know in our number system, we have 9 different digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now in computers, there's only 2 digits, 0 and 1. Now how can we map one thing into the other? All right. So I want to take you on a little detour here, a little context of like what's 65 anyway? What is 65? You know, if you go back thousands of years ago, where do numbers come from anyway, right? Numbers come from the early humans trying to give an assessment of how many things they saw. So if you see a group of sheep, it's different if there's only one or two from saying, you know, from 65 sheep. It's very different quantities, right? So people started trying to invent concepts for quantifying things, for the things that they saw in the world, right? And 65, it's both a quantity of sheep, but it's also a way of representing that quantity. It's really two things that are going on in here. It's something that says, oh, yeah, there are, you know, there's these many sheep, but now let me write it down. And the way that you write that down, it's something different from the fact that there are 65 sheep, right? And in fact, all through the history, there are lots and lots of different number systems, many different number systems. So here's an example. This first is a direct representation, and some cultures, you know, ancient cultures, there are traces that they did try to use that. So how do you quantify 65? You want to write down that you saw 65 sheep. A very easy way is just mark a little stuff for every thing that you saw. So you have, you know, 65, and you just have 65 little stuffs. That's it. Very simple. Um, Unfortunately, this doesn't scale very well, because if you have, you know, 65, you need this amount of real space, real estate in the paper. If you have 650, you know, it's a very long string. So this doesn't scale very well. So also around, you know, the just before the modern era, the counting is around the century 0 or around there. There are traces of societies and cultures who had already developed what's called compositional number systems, which means that instead of seeing a direct, no, one little line for every single thing that you see, you have a system that kind of composes and doesn't need so many symbols. So, for example, here's the Mayan representation. The Mayan, you know, they counted the little dots up to 4, and then the number 5 was a line. So if you wanted to represent number 6, you had 6 plus a dot. I mean, you had a line, which is 5, plus a dot, which is 1. And if you wanted to represent the number 9, there was 5 plus the 4 little dots. Okay, this is starting to compose, right? And if you had, for example, 11, you have 2 lines, which is 5 plus 5 plus 1. Same thing for, you know, 17 is 5 plus 5 plus 2, etc. They also had the concept of 0, which not many cultures had at the time. And moreover, when they wanted to represent very large numbers, the way that they represented them was actually they stacked them. So we write them, you know, right to left to right, right? They wrote it vertically. So for example, if you wanted to represent 241,083, this was, you know, the 3 is down here, and then the next up is 14 times 20, which is 80. And this what this means is that they actually counted the what is called their base was 20. Okay, so they had symbols all the way from 0 to 19, and then once they reached 20, that's when they kind of had a little column, another column on top, right? So that this is means 14, which is 14, and because it's the column on top, the row on top, it means that it's times 20. And the same thing here. This is 2 times 400, which is the next one. This is 10 times 8,000, which is the next one. So this is basically base 20, right? So if you wanted to write 65, it's 5 on the bottom, and then 3 dots times 20, right? So this is 65. And here the Egyptian representation of numbers. So Egyptians actually had a base 10, just like our modern number system. They just had different symbols for the number. So one, was this. This is 10. This is 100, 1,000, and this is like an astonished man is like a million. So they could count up to like a million, or on the order of millions. So if you wanted to write 46,206, you read it from right to left. So this is the 4, okay, of the 40,000. This is the 6 of the 6,000. This and the 2. This is the 2, and there's no tens, and then this is the 6. If you wanted to write 65, this is 6 tens plus 5 ones, right? So why am I saying this? So why I'm saying this is that the representation of numbers over time is something that evolved. It was different in many cultures had base 5, others had base 20, others had like the number system that we have now is base 10. What is this thing called the base? The base is the point at which the representation becomes compositional. So basically, when you have in base 10, it means that you have 10 symbols, and then from then on, you add an extra position that means, times the base, right? And then if you need more, you add another position that means time again, times the base, right? So you keep adding. That's a compositional system of numbers rather than just the no composition that doesn't scale. So the Mayans had a composition in base 20, the Egyptians had a composition in base 10. So our number system, what we all learn in school, is a direct descendant of the Hindu-Arabic number system. It was developed by the Indian mathematicians around the first, 4th century. It was adopted by the Arabic mathematicians around the 9th century. Spread through southern Europe. Remember, Europe at the time, the Romans were dominating around these times over here. So the number system that people used was the Roman system. I don't know how many of you know, but it's a different number system. But so this number system was adopted in Europe by the 10th century in southern Europe. Then it was brought to the rest of Europe by Fibonacci, the man himself, around the 12th century. And it basically replaced the Roman numerals in Europe by the 15th century. So they were gone by then. And so what is our number system? Because it's a base 10 system with 10 different symbols. These are the original Arabic ones, and these are the ones that we use now, so some similarity. Includes the concept of zero, again, as I said, this is something that not many cultures had, but the Hindus really got it, the idea of zero, which is nothing, right? It's an interesting system. So this is our number system. This is base 10. Our number system is in base 10, meaning that we have 9 symbols, and then when we run out of symbols for that particular position, we add another position on the side. That means now it's times 10, right? Because we're in base 10. So for example, if we want to represent 7,485, it's 7 times 1,000 plus 4 times 100 plus 3 times 10 plus 5 times. Everybody knows this, right? You learn how to do this in elementary school. And this is a little bit more, college level notation. What is 1,000? Well, it's 10 to the third, right? 10 to the power of 3. Yes. Oh, thank you so much, Nicholas. You are absolutely right. This is 10 to the 0. Copy paste badness on my side. I will fix it. This is 10 to the 0, the last one. So 10 to the 3, 10 to the 2, 10 to the 1, 10 to the 0. Any number to the power of 0 is 1. Okay? So this is our number system. Where does 65 come from? It comes from our number system. Okay, this number system, it happens to be base 10. It happens to have those particular symbols, but it's not by any means the only possible number system. And in particular, in computers, because the hardware is so much easier to develop if it only has 2 voltage levels, then it's number 2. It's base 2. Okay, it's the computers work in base 2 because the hardware becomes much simpler to develop. All right, that's the reason. So now that we know that now what does this two mean? It means that it's really two levels of voltage. Okay, the physical effect is voltage on transistors. That's what it means. So now it's up to us to how to represent the numbers, the quantities in the base 2 system for computers, because that's how computers are developed with these two levels of voltage. So how are we going to represent all the numbers that we know and love in decimal representation? How do we represent it in binary? Well, it's the algorithm, and I'm going to use this word carefully because I haven't talked about algorithms yet, but the mechanized process for composing in binary is exactly the same as the mechanized process for composing in decimal numbers. How does it go? So in decimal numbers, um, you look at the decimal. You start writing all your symbols. Okay, you have 9 symbols, so 0, 1, 2, 3, 4, 5, 6, 7, 9. When you run out of symbols, what do? You add another position to the left in this particular case, and now you start the right one starts again counting at 0, right? And now the left one stays at 1 for a while, right, until you run out of numbers again, and in which case you add yet another position and you do the same. It's always the same thing, right? So this mechanics is exactly the same as the mechanics for binary. How do you represent the different numbers in binary? You'll start with 0, and then it's the 1, and now we run out of symbols. Okay, there's only 2 symbols. Okay, if you run out of symbols, then you add another position, okay, which now is 1 because here was 0, and then you just count again 0 and 1 on the least significant bit, and again you ran out of symbols. What you add another position, okay, and you do the same thing again. You first change this one, you run out of symbols, you move this one to 1, you do this again, etc. Then you run out of symbols again, you add another position. Okay, so the way to construct this series of numbers that represent the different quantities is exactly the mechanism is the same. It's just that now we only have 2 symbols instead of 9. All right. So, but it's the way that you go from 0 to 1, and then what's 10, 11, 100, 101. It's not really 100, 101. It's 1, 0, 1, 1, 1, 0, 0. It's exactly the same thing. You run out of symbols, you add one more position to the left. Okay. And again, what are these in the computer? Again, it's not just abstract. This is real something physical. It's voltage in computers. You know, things that are stored in the computer memory, for example. That represent the some level of voltage or other, right? One or the other. Or it could be, the tile wall that you guys are going to have your homework this week, black and colors, black and white. It could be on and off switches. Just play around in encoding numbers around your house by putting your light switches on and off, for example. So these are physical quantities, right? That's the important thing. Once we have the power of the abstraction of numbers and 0 and 1, but that's not enough. We also need to have now the mapping of that abstraction into actual physical phenomena that then we can mechanize, right? And that's what makes computers so powerful, because now we find a way of mechanizing the manipulation of numbers. And that's what really makes computers so freaking powerful, is that on the one hand we are capable of representing the things that we care about as numbers, and on the other side we are capable of taking those numbers and representing them in some physical things that then we can manipulate with physics. Okay, that's the really amazing thing. We can build these machines that manipulate numbers, right, that represent something that is meaningful for us. Okay, so for example, I'm just going here for the number 13. How is the number? If you see, for example, 1101, what does that mean? How does that translate to the decimal numbers that you know and love? Well, it's the same thing, except that now it's base 2, right? So it's that bit, that digit over there, 1 times 2 to the 0. The other one, 0 times 2 to the 1. This one over here times 2 to the 2, and the final one on the left times 2 to the 3. right? And the coefficient here is always, in this case, is always 1 or 0, because there's only two values, possible digits. So in this case, it's going to be 8 plus 4. This is 0 plus 1, so we have 13. Okay, it's very easy to translate from binary to decimal, but the binary to decimal conversion is very, very easy. You can just do it with a table, if you that helps. For example, this number 1001011, this is in binary. What is this number in decimal? Well, it's super easy. Just write down another little row over here that has the powers of 2, right? So 2 to the 0, 2 to the 1, 2 to the 3, 4, 5, 6, 7, 8, etc. Right? Just write it down. And then if it's a 1, then it counts. Then if it's a 0, it's a 0, you don't count it. And so you end up with these numbers and you just add them all up. So this is going to be 256 by plus 32 plus 2 plus 1. There's your decimal conversion. It's very easy to convert to decimal. Okay? Any questions about this? Okay, this direction is very easy. If you have a binary number, knowing what the decimal representation is just doing this. The other way around is a little bit more complicated. So if you have a decimal number, how do you find out the binary representation? Well, one way that you want the brute force is just you write it down, from 0 to whatever that number, like 357. You write something like, like here. You continue to write it, but that takes a very long time, right? So that's just not very efficient. There is a mechanized procedure that given a number, you can find out what the binary representation is. And it goes like this. So you get that number and you divide it by 2. Okay? And you get two things. You get decimal to base 4, Daria. I will get to that. I have a slide to decimal to base 4. So first I'm going to explain decimal to base 2. So you divide by 2, 357, and you get two things. You get the integer part and you get the remainder part. So if you divide 357 by 2, you get 158 remainder, 178 remainder 1. Okay? And then you take this 178 and you divide it by 2 again. You get, in this case, 89, and the remainder is 0, okay, because it's divisible by 2. And then you take this 89 and you divide it by 2 again. Okay, again, you get 44, but in this case, you also get the remainder. Remainder is 1. And then you take that 44, divided by 2 again, you get 22, remainder 0. You get the 22 divided by 2, you get 11, remainder 0. And then you get 11 divided by 2, you get 5, remainder 1, etc. Until you get 1 divided by 2, and then you finally get 0, and then that's when you stop. And in this case, you get also remainder 1. Okay, so now how do you have to read this? You switch it like this. So this number, the most significant bit is the last one, and the least significant bit is the first one. Okay, so you end up with 1, starting from the bottom, 1 0 1 1 0 0 1 0 1. And if you do, that's right, Giselle. You totally got it, Giselle. Daria was asking, how do you convert for base 4? And Gisela said the same way. Do for binary instead, and divide by 2, divide by 4. She's getting ahead of me. Okay, so this is the mechanized procedure for getting a binary representation out of a decimal representation. Okay. So now let me talk about quaternary, and that is just something that I just threw in here, just to get you flexible about this idea that there is a difference between quantities and their representation, okay? And there can be many different representations for the same number. And so we know the decimal, now you guys also know binary, and just for fun, I'm going to also give you the quaternary, base 4, just because it's fun. It's not like computers use it. Computers don't use base 4 at all. But it's just for fun to give you some flexibility to really get this crazy concept that, the representation that we see of the number, it's not the number itself. Okay? So now let's play around this. Now in base 4 we have 4 symbols only. Okay, for example, 0, 1, 2, 3. In the case of your wall, it's not real numbers, it's different shapes. Okay, again, we can encode this in any physical phenomena that we want. And you can try to do this in your house, spread secret messages around by encoding things in different number systems. So 4 symbols, 0, 1, 2, 3. How do we represent them? So same thing. Okay, so here's our decimal numbers that we love. And now, how does the quaternary go? Again, the same thing. Start 0, 1, 2, 3. We ran out of numbers, right? Okay, it's time to spawn a new position and do the same thing. 10, 11, 12, 13. Okay, we ran out of numbers. Spawn a new. Actually, we did not run out of numbers. In this case, we still didn't go through the 2 on the second position. So now we have to go through the 2 on the second position, then the 3, and then we finally run out of numbers in this position, and then that's when we actually spawn another number. Right? So it's the same thing. Whatever we do with tens in the decimal number system, we do it with the binary number system, we do it in the quaternary, any base number system. It's the same procedure. So for example, this number over here, that is 13 in decimal and 31 in quaternary, how do you, if you given the 31, how do you know the decimal representation? Well, this one is easy. It's the thing. So it's 1 times 4 to the 0 plus 3 times 4 to the 1, 13. So 31 in quaternary is 13 in decimal. So again, this direction is very easy. Given the quaternary number, how do we find out the decimal representation? Again, same thing. You put a little row over here with the powers of 4. This now it's the power of 4, right? And then you just okay, this is a 2, so it's 2 times 1. This is a 0, so it's 0. This is 16, so it's 16 times 3, right? And this is 64, and then it's 64 times 2. You get this, and then you add these numbers, you get 178. So this direction is very easy. How do we convert the other way around from decimal to quaternary? Well, it's basically the same as the decimal to binary, except that now instead of dividing by 2, you divide by 4. So you have 357 divided by 4, you get 89 with remainder 1. Then you take the 89 divided by 4, you get 22 with remainder 1. And then 22 divided by 4, you get 5 with remainder 2. And then 5 divided by 4, you get 1 remainder 1. And then 1 divided by 4, you finally get 0. That's when you stop. And this one's remainder 1. So this, it was unfortunate that I got a number that reads the same way from left to right and left to left. But don't forget that the last one is the most significant bit, and the first one is the least significant bit. Okay, so this is the representation of 357 in quaternary. All right? Any questions? Okay, so what is the bottom line? So the bottom line here is threefold. So basically, electronic circuits are much simpler when they deal with just 2 values of voltage. It's just more reliable than if they have to distinguish between more values of voltage. So they have 2 values, 2 symbols. And that's why in computers, all the numbers are represented in binary. Okay, whenever you see videos about computers, you see these things about zeros and ones. Well, it's just because the way that the hardware is designed is just much easier if it's just 2 values of voltage instead of many. Okay, so now we are in base 2. We just have to represent numbers in base 2. It's not a big deal. But again, decimal and binary representations are just 2 among many possible representations of numbers, including the Mayans and the Egyptians and all the ancient cultures that have all sorts of interesting things. I am Noel. I'm going to go to the project. So we can represent numbers and therefore any information with any number of symbols in any media. Okay, that's the interesting thing. So what's the big picture? It's these 2 levels. So you get text. Let's start with text. Could be images. So you have text, for example, "Hello World," all right, exclamation mark. This is encoded using the ASCII encodings into a series of numbers. So capital H is 72, E is 101, L is 108, etc. So this is a series of numbers that encodes that word using ASCII. That in turn is represented in binary representation in computers. So here's the binary representation of those numbers over there. Okay, this train of zeros and ones. And what is this really in computers? Well, it's just these two values of voltage. So for example, if you have hello world exclamation mark stored in your program, in a computer somewhere there's hello world, for example, in your text file, you write hello world, that is going to be stored somewhere in memory. What is that? Well, it's this number represented in some physical effect, like voltage, for example. So you have, transistors in memory. Some of them are on and some of them are off in a way that reflects this number over here. That's what it means. Okay, so we go all the way, all the top text that we understand, all the way to physical things that are, of which there are only two symbols of them, and that represent that text that we are, that makes sense to us. Okay, so this is the stack, all the way from the things that make sense to us all the way down to the physics. Okay, so this is the lecture that I wanted to just make sure that we have the right model about what's going on and why binary is important. I want to talk a little bit about your homework before we go breakout for the class assignment. So let me talk about what you need to do for project 2. So for project 2, the first part, there's 3 things. The 2 first things are, I think, super easy. Okay, so the first thing is the easiest of all. You probably all have seen that you have a new devices in your 3 houses, which are these tile walls. And actually, let me go here and just tile wall. Let me put the tile wall here somewhere. Okay, let me. All right, let me go here. Just sit down as usual, and you will have these 2 tile walls. One is just a binary wall, so if you click on these tiles, they switch between black and white. So it's just 2 things. And so what you need to do is to encode your name using ASCII or extended ASCII encodings, starting from the top. So for example, my name is starts with a capital C. The capital C, according, I give you a link for you to look up the binary encodings. The capital C is the number 67, which is this. It's 4. It's 67 is this number over here. All right, there. This top row is the number 67. Okay, so if you look, it's 2 to the 0, 2 to the 1, 2, 3, 4, 5, 6. 2 to the 6 is 64. Yeah, and then plus 3. Okay, so if your first and last names is more than 16 characters, it's okay. Just stop at 16, whatever it was. Okay. So I'll also, so I'm writing Christa, and then the space should also be included. All right. If your name has a dash or something, you should include it too. If your name has like a special accent, you should look it up. So you should use extended ASCII that also has those characters with accents. Okay. So this is super easy. The only thing that you need to do is to look up the hold on. Look up this extended ASCII encoding that I linked from here. There it is. And then find the character that you want. For example, R. Here's R. Here's the binary representation of R. Okay? And just, type it in the tile wall. The extended ASCII is down here. So if your name is, for example, has a accented A, so here's the accented A. The accented A and C and whatnot. So they're all here. Okay, these are their representations. binary representations. Okay? Any questions about the binary wall? So Noel's asking if it saves when you finish. It doesn't save, so it just stays here until somebody comes and clicks. So what I suggest is that after you're done, just take a picture. So what you need to turn in is just a picture, all right? So you just take a picture, Biv, and I'll answer your question in a little bit. So take just after you're done, take a picture. Make sure to capture it, and then once you capture it in the picture, then you're done. Okay? And Vivian asks, where can I find the link to the chart? You can find it right here on the homework. Here. In here, the first line of the homework. Using the binary, the black and white tile wall, write the first 16 characters of your name binary using extended ASCII encodings. It's right there. Okay, just follow this link. This is the table that you want to look up. All right? Any more questions about the black and white wall part? Okay, so then I'm going to go to the second part. The second part is quaternary. So now it's this other wall over here. This wall has four things. So it has the square, the white square, and then it has a kind of a lampshade kind of thing, and then it has a sort of prism thing, and then it has a sphere. So it has four symbols. And in the homework, I tell you which one is supposed to be which. So the square is supposed to be a 0, the lampshade is supposed to be a 1, the prism is supposed to be a 2, and the sphere is supposed to be a 3. Okay? And now the goal is to encode again your name, the first 16 characters of your name, using base 4. Okay? Now, base 4 is not something that you can find directly in this ASCII table because, as I said, base 4 is not very useful. It's not very used. Is there only one tile wall? No, Mega. There are two. There are two tile walls, and if you're missing a tile wall, let me know. Something went kind of wrong on zone 1, the green zone. Some of the tree houses at some point did not have both of the tile walls. I think I fixed all of them, but if you're still missing one of the tile walls, let me know. So the quaternary encodings is not something that you find in standard ASCII tables anywhere because the quaternary is not used very often, just used for academic exercises like this one. So what I suggest, the best way of doing this, you can do whatever, you can do whatever you want. You can do, get the number, for example, if your name has a capital A, here's 65, do your calculations and figure out what's the representation of 65 in quaternary according to what I just explained. Divide by 4, take the remainder, stuff like that. You can do that. Another way that you can do is just grab this table. Okay, come here, grab this entire thing, copy paste this, all right, which is what I did, I confess. Copy paste this into like an Excel spreadsheet, okay, and then add another column. And then on that column, you're going to do basically something like this column over here. Just write down the numbers in quaternary. Just write them down, just like they are here in like binary and hexadecimal, which I didn't talk about. But so there's like 3 columns over here, actually 4. The decimal notation, the hexadecimal notation, the binary notation, HTML. So just add another column and by hand, by yourself, just create the sequence of the representations of these numbers. So this is here, start at 0. This is 0, then 1, 2, 3, then 1, 0, 1, 1, 1, 2, 1, 3, then 2, 0, 2, 1, 2, 2, 2, 3, then 3, 0, etc. Okay, and then when you need to look it up, just look up on your Excel spreadsheet what's the representation of your character in quaternary. Does that make sense? All right. So Let me just mention the final part of the homework is again a little program. So this part is to use the computing machine. So you're going to use the same computing machine that we used for homework one. But in this one, I am actually giving you the program that implements this algorithm over here. This one. So the one that implements the conversion from decimal to binary. This is the program that implements that mechanization. Okay, and I have enough comments over here that hopefully you'll be able to follow. And your goal here is just to change this program so now instead of converting from decimal to binary, it converts from decimal to quaternary. Okay, this should also be very easy because I'm giving you already the entire program. Okay, you just need to understand it and change a little bit, couple lines of code here that to the quaternary conversion. Okay, does that make sense? All right, so we have 10 minutes or whatever, not even to. Is there any resources on before? Um, So you probably can find stuff out there on different bases for numbers on the web. If you find it, you probably you'll if you search for it, you will find it because there's people who like all sorts of obscure topics. But I think that you should be able to understand just by looking into the slides, my slides of the lecture, which I have. Richard, hold on. I will reply to you. So the slides of this lecture are available on Canvas. Let me show you. They are right here. If you go to the syllabus, and then if you go to today's lecture, which is this one, lecture data representations, you will see. I will post the video here, but the lecture slides are already there. So if you need to recap again, just go through the lecture slides and I think this should be enough for you to understand the quaternary representation. But I'm sure that you will find it out there on the web too. Okay, so Richard Wong was asking, what if I create my own program? Can I turn that in instead? Yes, you can, of course, absolutely. If you prefer to, implement your program in another way, this conversion program in another way, you absolutely feel free. As long as it does the same thing. You probably by now all know that there's many ways of doing the same thing in programs. So if your program is different and does the same thing, that's great. All right, so just one thing that I would like you to do, just to get these mechanics out of the way. Let me show you here my window. Let me remove this out of here so that you can. On the stage, there's these two objects, these kind of yellowish objects, one on the right side and on the left side. The same as last week, do the following. Before you start sending up, let me explain. Right click on one of them, choose more, choose take copy. All right. This will give you an object in your inventory under the objects folder that has the name 2021-01-28. That's today's date. And so once you get to your treehouse, drag this thing onto the lawn of your treehouse. Okay, this ended up somewhere in ether. Oh man, now it's stuck on this invisible wall. So this will end up on your lawn. Okay. And then once you have it on your lawn, right click again, say open, and then copy to inventory. Okay, when you copy to inventory, there will be a folder and something, one of the text things happen, open, and then it will give you the instructions for what you should be doing. Okay, just a little exercise, and I will try to call you back. Although if you guys stick around, I will call you back so that we can all talk about this exercise. Even though it's probably beyond the time limit of the class, but if you're around, we'll just finish this off, okay? So don't forget to place this in your lawn, including the students who are not here right now. Please place this in your lawn today, because tomorrow morning I will go make a visual inspection, and the tree houses that don't have this object in the lawn, I will mark you absent. What's in the class exercise? So it's just for you to exercise the tile walls. All right. So I'm just asking you to write like "Hello World," just just basically just to get you started on your homework. So that if you stick around another half an hour, you will be able to actually finish your project too. Okay, Noel wants me to go through the peer reviews. All right, so the peer reviews, let me just go, for those of you, either you can watch it right now or a little later, because it's going to be in the video. Let me go here to the peer reviews. And it's one of those things that I don't have the same view in Canvas as you do, but I'll tell you what this is. So if you go to the assignments, and if you go to the computing machine assignment, somewhere here on your right, oh, you are not seeing, I'm sorry. All right. Somewhere if you go to the, the homework specification page, somewhere here on your right, you will see something related to peer reviews. And it's not going to be the same thing that I'm seeing here, because I have the instructor view, you guys have the student view, but somewhere here there will be peer reviews. And so if you follow this through, and I'm not going to follow here because otherwise I would be disclosing, but if you follow this link, you will see the students who have been assigned to you. Okay, and then you can download their submissions, and then what you want to do is open their submissions. It should be text files in there. You should copy those programs and paste it into one of the note cards. So you go here, on your viewer, in here, you just go to the note cards object for a folder. You create a new note card over here, and then you go copy paste, from the student's text file on your computer into here. You paste it here, and then you drag this into the computing machine to see how it works. Okay? Is that clear, Noel? All right, cool. Oh, and don't forget to also check your attendance over here. Okay, Richie is asking, what comments should we leave for the peer review? Um, so if you find that the programs will work, so for each program there's there's a rubric. One is for correctness, the other is for completeness. And if you find that the program is all according to spec, you just say, this works according to the requirements. It worked for all the test cases that I used. If you see that the program doesn't work for example, doesn't accept the zero, doesn't do the right thing when you enter zero or something like that, you just say, this doesn't work in this situation. It didn't work, when I entered this sequence of numbers or whatever. So you just say if everything works, you just say everything works. If something doesn't work, just explain what is it that it doesn't work. Okay? Okay, so there's another question coming from Francis. How should we go about writing our peer review if the submitted file cannot be opened? I guess you just have to say that you were not able to open the file. I don't, maybe the student has packaged their program in some weird file format. Just say that you cannot open that kind of format. Okay. Another question from Raya. My monitor for the black and white tiles isn't working. Okay, Raya, I will try to help you after the class. Okay, I'll go to your treehouse and I'll try to do that. See what's going on. Okay, Brendan has a question. Can you do an example of quaternary for capital B? All right. Quaternary for capital B. Let me put a wall here. And of course, this question has been asked by Brendan, whose name starts with a capital B. So let me go here and put the tile wall here. All right, so let's see. So capital B, let me find my Excel spreadsheet because I don't feel like doing all those calculations. But I can tell you the calculations, what calculations you should be doing, okay? If you want to do the calculations. So the calculations that you should be doing are this. You go to the ASCII table. So capital B is here. It's 66. All right, so 66 divided by 4. All right, calculator here. 66 divided by 4, it's 16. Reminder, I'll do it up. I'll do it on this last row over here. So it's 16 reminder 2. 16 reminder 2. So the least significant bit is 2. So that should be, hello, what's wrong with this thing? Hello? Oh man, what's going on in here? Oh, I'm not sitting now. What the heck? Hold on. Stand up. There. All right. Let's sit down here. So reminder 2. So reminder 2 is this is 0, 1, 2. All right, and then it's 16. So now you divide 16 by 4. It's 4. Reminder 0. So this is 0. And then 4 divided by 4 is 1, reminder 0. And then you have 4 by 4 is 1, reminder 0. And then 1 divided by 4 is 0, reminder 1, I believe. So this should be a B. On this bottom here, if I did the calculations correctly, this should be a capital B down here. Okay, Brennan? The screen is stuck on the tab. What is tab? Table. The screen is stuck. Oh, I'm sorry. Okay, there. It's so I was doing on this last row over here, down at the very last bottom row. This is the one that I'm doing. So I think if I did the calculations correctly, this should be a capital B. I can double check on my Excel spreadsheet. Let me check. All right, so capital B should be 1002. That's right, 1002, capital B. Okay, Brendan, did you see that? All right. Yeah, so I would suggest that you do what I did. It's just, grab this as an Excel spreadsheet and just add that column and just write down the numbers in quaternary. Then it's much easier to look them up. Okay, I'm gonna call the class is dismissed. I'm gonna call everybody. If you want to stick around, we're gonna go together through the solutions of this in class exercise. If you need to go, just go. But I'm going to call everybody back to the auditorium. Um, all right. So I hope that some of you are still here. And if you are not, maybe you will watch this video a little later. I just want to wrap up the in-world, the in-world exercise, the class exercise, just to make sure that we're all on the same page. So the first thing that you needed to do was to, in the black and white style wall, was to write "Hello World." Okay, so how are we going to do this? Very simple. We're going to go to this URL that I just pointed to, which is these tables, the ASCII table, this one over here. So we're going to find out the capital H. There's the capital H over here, which is the number 72, and it's binary 0100 So the black is 1, the white is 0. Um, so hello world should be 0100100. So that should be capital H. The next letter is E, small e, lowercase e. Lowercase e is 101, which is 0, 1, where is the E? Before I forget, 0, 1, 1, 0, 0, 1, hello, slow. So many people here. Hello? Oh man. Come on. Work. There. Okay, so E, where's E? There, it's not, no, this one. 101100101. All right, this is the E. The the L is 0, 1, 1. Oh man, stop acting up. What's wrong with this? Too laggy, yeah. Yeah, I guess too many people are running these scripts. There's a script in each one of these little tiles. Gonna come back again at night. All right, so L is L. Oh, come on. There, 0, and then 1, and then 1, and then 0, 0. So this is an L. There are two L's. All right, and then there's an O, which is 0, 1, 1, 0, 1, 1, 1, 1. Okay, this is an O. And then a space, so the space character, according to the table, is number 32, which is just 001. This is the space character, and then world, capital W. Capital W is 0101. Oh, come on. All right. I guess reaching the limit of how many scripts I can hold in this thing. I may need to remove some of the older machines. Come on. All right. So 01, 01, 01, 1, 1. Okay. So this is the capital W. The lowercase o is 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. R is 0, 1, 1, 1, 0, 0, 1, 0. L 0, 1, 1. I think it's this one. I lost track. WORL. Okay, 0, 1, 1, 0, 1, 1. 0, 0. Okay, so and then the D is 0, 1, 1, 0, 0, 1, 0, 0. Okay, and then exclamation mark is the number 33, which is 0, 0, 1, 0, 0, 0, 0, 1. Okay, so this should be reading Hello World if I got it right. And then the other thing, the other part of this in class exercise was just to write down these numbers, literally. Just so this is there are no encodings here, just to get the mechanics of this right. So it should be 0, 1, 2, 3. That's right, genial. It's like a Picasso's painting. In fact, there are some artists out there over time, especially in the 20th century, that have done really interesting art with these kinds of encodings. There's all sorts of creative things that can be done if you just add a little bit of math. All right, so the second number is 3, 2, oops, 1, 0. The other one is 0, 0, 0, 0. Oh, come on. You can do it, little wall. Come on. All right, 0, 0, 0, 0, etc. So the second part is it's just easy for you to get acquainted with these symbols. All right. So I guess that's it. Does anybody still have any questions? I know we're way beyond the end of the lecture now. Okay, so if anybody is missing a tile wall or something, just send me a message on Piazza or here. I'll go and fix it for you. Otherwise, class is dismissed. Have fun with your paintings, and I'll see you in Piazza, and I'll see you next week here. Bye.